So here we will be learning about spherical mirrors. So what is meant by spherical mirror? See this, I will show you a sample of a spherical mirror. This is it, right? It's actually a it's a cross section is circular, but it's a spherical mirror. What does that mean? That suppose you have a sphere. If you have a sphere like this and you cut out a portion of the sphere, then this cut out portion, this acts like a mirror. This one is the mirror. See from the front view, from the front view, see this is it, right? This is it from the side view. This is what the side view is. You are looking from here. It looks like flat because the radius is very large, and from the front it looks like a circle. Okay, so this part, I mean this reflecting part of the mirror, this reflecting portion is known as the aperture. And see aperture size, you know, those who are interested in photography, they deal with aperture. The size of the aperture is actually the diameter of this circle, this. So this diameter is aperture size. In photography though, you have lens, in camera you have lens and aperture size of the lens. This is for mirror. So this is it, this is a spherical mirror, and this center of the reflecting surface is known as pole. So here in the diagram, this, see from the front view, this is the pole, in the side view this is the pole, P for pole. And this mirror is part of a sphere of center C, right? This, I mean this cutout surface mirror, it is part of a large sphere. Now see, this is P, this portion is cut out here, right? Now this radius of the sphere R is radius, it is known as radius of curvature, radius of curvature of the mirror. So it is the radius of the sphere of which this mirror is a part. Now this C, center of the sphere of which this mirror is a part, is known as center of curvature. Center of curvature of the mirror. Now this, the line joining C to P and this extending throughout, this line is known as the principal axis. This line, right? This line is known as principal axis. Okay, so there are basically two types of spherical mirrors. One is the concave mirror, concave, another one is the convex mirror. In the concave mirror, say this is a part of the surface of the sphere. See this is the concave mirror, where the reflecting part is the concave part, and this is the convex mirror where the reflecting part is this, and this is a silvered part. This part is a silvered part. Say for this mirror, this part is a silvered part, it is shown by this, and this part is the reflecting part, the shining part where light reflects. So this is concave mirror and convex mirror. Now we'll define the focus and focal length. focal length of the mirror. Now focal length of the mirror is represented by f. Now f is equal to fp actually, where I'll tell you f is the focus. F is the focus of the mirror. What is the focus? Focus is, say, the parallel beam of light, in bracket, parallel to the principal axis, converge there may be two types of focus. When converge at focus for the concave mirror, parallel beam of light parallel to principal axis converge at focus for concave mirror, and appear to diverge from focus for the convex mirror. Now here I will show you how. Say this. So which is the principal axis here? Say for this concave, this is the pole. For convex, this is the pole, this is the center of curvature, this is the principal axis. For the convex one, this is the center of curvature and this is the principal axis. And say parallel beam of light parallel to the principal axis are incident on the concave mirror. So I will draw this light ray. Okay, see, this light ray will be normally incident on the surface of the mirror. This is the case of normal incidence. While this, for this, there should be drawn a local tangent, right? Now this local tangent at this place and the local normal here will pass through the center of curvature. Always at all points the normal to the surface of the sphere always passes through the center of curvature. So here it will follow the angle of incidence theta is angle of reflection theta. So here it is. So this is the focus for concave mirror. So which one is the focal length here? See f. See, if you see this ray passes through this principal axis and the ray here will retrace back its own path. So this is the focus, or you can say this is the image for the object at infinite distance. So f, so this is small f. The distance between focus to the pole is the focal length. Now let us see this case for this convex mirror. See, one of the light rays here, so obviously the local tangent and local normal, so this will retrace back its path. Okay, so light has to come from this way. Now there is one more light ray I will draw here. So at this point the normal, as always the normal will pass through center of curvature. There it is. So this is the normal, and it will obey obviously the law of reflection of light. So this is theta, so this is also theta. So here it is. There. So this is the focus. This is the focus for the concave mirror. So see, according to definition, parallel beam of light, say these two light rays make a beam. There are more light rays also. We'll work with two light rays. Parallel beam parallel to principal axis CP converge at the focus for concave mirror and appear to diverge from the focus for convex mirror. Appear to diverge, why? Because if you see here, is this light ray here, this light ray and this light ray. So the human eye cannot follow the curved path of light. It will see that, okay, or we will see that this light ray and this light ray, obviously light will appear to come from this point. So this is the focus for the convex mirror. This is for concave, this is for convex mirror, and for the convex mirror this is the focal length. Okay, remember this is the radius of curvature. Yeah, right. This is the radius of curvature. This here, right? The center to the pole distance is radius of curvature. Okay. So you know there is a relation between focal length and radius of curvature. F is equal to R by 2. If you know about similar triangles, then we can prove it. Now this F equal to R by 2, it is valid for certain conditions. Condition is the aperture size of the lens is small. Now what is small and what is big? It is small compared to the radius of curvature. That means it's more or less like a very flat lens. See, this is a curved surface, but you can hardly guess whether it is curved. Looks like a flat surface. So for this type of mirrors, it's true. So that means we can say for paraxial light rays, that is the rays close to principal axis, paraxial light rays, or you can say that small aperture size, small aperture mirrors. Obviously small compared to radius of curvature. If aperture size is small, it is guaranteed that light rays will be close to the principal axis, because the diameter of aperture is itself very small compared to radius of curvature of the mirror. So this diameter of aperture is this. So if this diameter, right, this diameter from this point to this point, distance is much smaller than radius of curvature, then obviously the light rays are close to principal axis. Okay. So that is the pole center of curvature. Let's prove this. So this is the incident light ray and this is the normal. Suppose this point is A, so it will follow the laws of reflection, and this is the focus. And you see these two lines are parallel lines, principal axis and this. So this angle, and this is the transversal, so this is also theta. So this triangle, so triangle ACF is an isosceles triangle, So that means CF is equal to AF, I mean this side is equal to this side, and A is close to P, implies AF is, this is a sign of nearly equal to, AF is nearly equal to FP. Therefore, see, from these two conditions, so from this condition, and this condition. See, we can say that CF is nearly equal to FP. That means these two are equal. So the focus is halfway between the center and the pole. The center of curvature and the pole, these distances are radius of curvature, and focus to pole is focal length. It's the same for the convex mirror, right? It is exactly same for the convex mirror. You try out and draw the diagram and prove this for convex mirror. That is a work for you. Now we will be drawing several ray diagrams. Ray diagrams for spherical mirrors. So let's take first concave mirror. Concave mirror. So there will be several cases we will be dealing with. First case, principal axis. So draw for point objects first. So that is the concave mirror. This is the silvered side, and this is center of curvature, and this is focus. Okay. First, suppose there is a point object O. The first case, point object beyond center of curvature, beyond C. Okay. So just think about the light rays. One light ray will go here. This is the pole. One light ray will go here. Normal incidence, it will come back. And this light ray, here it will strike the mirror, and this is the normal. This is the normal. So you see, this angle is equal to this angle, both are equal to theta, and this will be the image I. So this is for point object. Okay. Now the next diagram we'll draw is for and say extended object. Extended object beyond C. So we will learn the technique of drawing ray diagram. That's F, C, and this is an extended object. It is shown like this. This is the head and this is the feet. Suppose a person standing, for him or her, this is the feet and this is the head. So the technique for drawing the ray diagram is like this. Let me extend it a little bit beyond. See, just concentrate on two light rays. One light ray will go through the center of curvature, and the light ray going through that, passing through center of curvature, will obviously be perpendicular to the surface, right? Because any radius to the sphere is perpendicular to the local tangent, or any radius or any line from center to circumference is normal to the surface of the sphere. So whatever this light ray, this will go and come back via the same path and continue its journey here, right? And say for, and one more light ray. So one light ray through C, one more light ray through will be parallel to principal axis like this. So the light ray parallel to principal axis, as we have seen what focus is, so that will pass through the focus. So we got that for this point, this is the image. If this point is object, then this is the corresponding image. And obviously we know for this point, it is join point to point. So this is a point, say A, this is point B. For point A, the image is A dash here, A prime, and for B, the image is in the same location. See, it will be vertical, so there it is. This is B prime. So for this object, this is the image. Okay, what is the nature of this image? So here the image is, now we will analyze the characteristics of the image. So the image is, it is smaller, right? It is, as you see, it is smaller than the object. So we write it is diminished, and what else? Inverted, and what about real and virtual? Obviously the light rays actually meet at the point, so they realistically meet at this point, so obviously it is real image, so you can cast it on a screen. So the image is real, and location obviously between C and F, that is evident from the diagram itself, between C and F. So these are the characters of the diminished and inverted, real, and between C and F. Okay. Now next we will draw for extended object. Extended object, last one was between, now beyond C, now it will be between C and F. This is the principal axis. Concave lens, silvered side. This is pole P, F, C, and the object will be here. It's be at between F and C. So here. Okay. So again, we have to concentrate on two rays. One is through center, and one is parallel to the axis. So through center, just join this point with the center, extend this line, so the light ray through here, it will come back like this. It will come back like this, and one more light ray parallel to principal axis, that will pass through the focus, right? Parallel to principal axis, as we have defined focus, so obviously it will pass through the focus. And let us extend this. Yes, so it will hit extend this principal axis. So there it is. So the image of this point is here. Image of this point is here. Similarly, the image of this point will be here. It will obviously lie here on the axis. So for this extended object, this is the image. So in this case, as you have seen, what can you say about the characters of the image formed? As in the last case it was diminished. No, here image is magnified, then obviously inverted, and obviously real, because realistically you have this points or spots where light converge, and it is beyond C. It is beyond C. In all these cases you will find one thing common. See, if the image is far away, see, whichever is far away is bigger. Be rest assured about that, whichever is far away is bigger. See, one thing I'll show you, that this is one of the light rays, right? From here, one of the light rays will hit the pole. One of the light rays will hit the pole, and obviously it will pass through this. See, we are drawing the ray diagram with the help of these two rays. Doesn't mean that there are two rays only, many rays. So all the light rays from this point will go and meet at this point. So this is one of the light rays. So as you see here, we'll also discuss in details this thing. As you see here, only for this object and this image. Now there was this pole, right? See, this ray, this light ray, this light, this is one of the light rays which will hit the pole and come back in this way. This was the pole. Okay, so obviously this angle is theta, this angle is also theta. So if you know of similar triangles, you know this height divided by this distance is this height divided by this distance. So height is proportional to distance, right? For similar triangles and right angle triangles also. So object height divided by object distance. Object distance means distance of the object from the pole is equal to image height divided by image distance. By the way, so some more. Next case will be extended object. Extended object between F and P. Extended object between focus and pole. There it is, concave mirror, pole, focus, center of curvature. And if there is an object like this here, let us draw the light ray from this object. So this one light ray will be from this point, so see, extend it, so this, and it will come back via same path, because any line through center is normal to the surface of the sphere. Now this light ray, consider this light ray, this will pass through the focus, this will pass through the focus, and see, if you draw the ray diagram properly, this is it. So I'll again mark these things, this side, this. Okay. So if you extend this, so from here, if someone observes the light rays, if you look at the light rays, so it appears to come from this point, right? It appears to come from this point. So for this object, this will be the virtual image, right? This will be the same way. For this point, you can find the image will be here, right on this vertical line. So for this point, this is the image. So here, now here I will show it by a dotted line, because there is nothing here actually, right? In reality, this thing doesn't exist, or we say that the light rays appear to diverge from this point. It does not really diverge from this point, as these are the reflected light rays. So this is a virtual image. So about the characteristics of the image, we can write image is, first point, it's magnified, then it is erect or upright, then is virtual, and it is on the other side, Now there may be a special case where the extended object happens to be standing on the focus, on the focus here, maybe, or on the center of curvature. Extended object at C, center of curvature at C. So let's see what happens. Pole, focus, center of curvature, this is the object. Now it is hard to draw a light ray from here to here, because you know the aperture size of the mirror is not so large. So we'll settle down with this case. This light ray will pass through the focus this way. Okay, now let's draw one more light ray through the focus. So if you draw this light ray through the focus, then obviously it will go from here. So this point exactly is this way. So this is the image of the, sorry, it's not dotted, it's a real image. So if object is at C, then the image is of same size and inverted, then real, and on C, or at C rather. Now if the extended object is kept at F, then what happens? Let's see. There's the mirror, concave mirror, pole, focus, center of curvature, that is it, object. Now draw one light ray will be one light ray, it will pass through the focus, and one light ray passing through center of curvature. This way it will return via the same path through C. So in this case, where is the image? The image, you can say it is here or here. You can say it is real or virtual, but actually we say the image is at infinite distance. No point in saying which side, is it on this side or on this side, and you know why there is no point in saying it, because the light rays will never meet. Let us discuss the ray diagrams. See, this is a ray diagram for a convex mirror. So here we go, this is the convex mirror. There is the principal axis, this is the pole, center of curvature, this is the focus, and this is the case for extended body or extended object just near the mirror. It can't be on the right side, obviously. So let's draw the ray diagram. So we will draw one light ray passing through the center of curvature C. It cannot penetrate the mirror, so this right side we are showing by a dotted line. I mean the light ray is directed towards the center of curvature. So as you know, this line is perpendicular to the surface of the mirror. So that is a case of normal incidence, and the light ray will go back via the same path. Okay, so let's see. Here it is, perpendicular to the surface. Now let's draw one more light ray. Here it goes, parallel to the principal axis. Should be exactly parallel. Yeah, that's it. Now as per definition of focus, this light ray will appear to come from the focus. So there it is. So this point shown is the image for the topmost point of the object. See here, topmost point of the object, and for the downward point, the lowest point, the image lies on the principal axis. So there it is. This is the image for the object, and it is shown by a dotted line because it's a virtual image. Okay. See this one. Now let us write about characteristics of the image. So the image is, what are the characters of the image? See, one by one I am writing down. Is diminished. Just by looking at the ray diagram you can see the image is diminished. And next point, the image is inverted or erect. It is obviously erect, as you see from the ray diagram. Next, obviously image is virtual because light cannot meet at the right side. Obviously the image is on the other side of the mirror. As you can see from the diagram, obviously. So the use of the convex mirror is in looking glass of a car. Okay. So in the looking glass of a car, you see the image of the cars behind your car, and the image looks diminished and erect also, as seen in the diagram. Now I'll be drawing a diagram of the car. The view of the driver, there is the steering, and this to the right we have right hand drive. So see the images of the bus, the big bus looks like a little toy bus, and the cars all look very small. As you can see in the ray diagram, the image is erect and virtual on that side, diminished also. That is why the field of view of this mirror is large. That means in a small space, in a very small mirror, see, look at this diameter. The aperture diameter of the mirror is very less, right? Obviously here we use a rectangular mirror, spherical mirror, but its size is very small. Now let's see in this page. Convex mirror has a large field of view. That means in the small space, in the small dimensions of the mirror, as I told, you can fit in many things, and this means the field of view of the mirror is very large. There it is, a ray diagram. See the extended object between f and, okay, this one is for the concave mirror. Here also you can see image, but it is extended image, I mean magnified image, and erect also. So in the looking glass of a car you cannot use a concave mirror. See, use of the concave mirror when an object is between focus and pole is the shaving mirror, is as shaving mirror, because when you are shaving you have to see the details of your face. See, in the diagram I have shown, this mirror is in front of the person and he sees his face bigger than normal. Okay, so now I've got two mirrors in my hand. One is concave, one is convex. Simply by looking at those mirrors, they will look like flat, but they have a spherical shape. One is concave and one is convex. and I will demonstrate here. See, look at this mirror. This is the phone with which I am recording on the tripod, and this one to the left side is obviously the convex mirror, because the image formed by convex mirror, as you can see, is diminished. See, this is me. You can see my face smaller, and the size of the phone and the tripod, and see, you can see lot more things in the room, because this convex mirror has a large field of view. Now let's see the concave mirror side by side, both side by side. See, this concave mirror, you are seeing magnified image. Yeah, here it is. You have to bring it close, right, between focus and pole, then only you can see magnified image. See, the mobile camera looks to be so big. And just to have a contrast, see the contrast, just by its sides, rather, the convex mirror shows the image very small. Look at this, the size of the mobile phone, mobile camera. Left one convex and right one concave mirror. Just I can keep it here, right? Convex mirror. No, that one was concave by mistake. Yeah, this is the concave mirror. If I keep this concave mirror, you can see what I am doing in this recording session.